Let's talk a little bit about carboxylic acids. As a functional group, a carboxylic acid is composed of a carbonyl, and attached to that carbonyl carbon you will have a hydroxyl group. Now we don't name these two groups separately, so for instance I don't say that I have a carbonyl and a hydroxyl group. We take both of these groups together as a whole and name this functional group a carboxylic acid. The carboxylic acid that you're looking at is formic acid, and it is the simplest of carboxylic acids, or in other words, it is a one-carbon carboxylic acid. On the opposite side of the hydroxyl group, attached to the carbonyl carbon, we have a hydrogen. Most of the time, this is not going to be the case. Most of the time, on this side of the carbonyl, you're going to have a carbon. This is an example of a carboxylic acid that's more typical, where you have both a carbon and a hydroxyl group attached to the carbonyl carbon. This acid is acetic acid. A 5% solution of acetic acid in water is vinegar. In more general terms, we can just say we have a carboxylic acid group with an R group attached to the carbonyl, and the R group could represent anything. Or you could say an AR, or an aryl group, attached to the carbonyl carbon, and that's meant to represent any aromatic group, if you wanted to be a little bit more specific. Let's review what we know about the bonding in carboxylic acids, and let's look at acetic acid in particular. Our carbon and our oxygen of our carbonyl group, you may recall, are sp2 hybridized. Our carbon has 3 sigma bonds, here, here, and here. And those sigma bonds are made up of the overlap of the sp2 orbitals of the carbonyl carbon with the sp3 orbital of this carbon, an sp3 orbital of this oxygen, and with an sp2 orbital of this carbonyl oxygen. The pi bond is made up of the overlap of the unhybridized p orbitals. This means that the carbonyl carbon has the trigonal planar geometry, and you may recall that the ideal bond angle for an atom that is trigonal planar is 120 degrees. You also may remember that when you're talking about heteroatoms with lone pairs of electrons, we usually don't see that idealized bond angle, and this is due to the repulsive forces of the lone pairs of electrons, in this case on the oxygen atom. So here we see this bond angle of 110 degrees, so it's pretty squished from the ideal 120 degrees on the basis of the repulsive forces between the non-bonding electrons on this carbonyl oxygen and the bonding electrons on the carbonyl carbon. So we have a little bit bigger angle over here on this side due to these repulsive forces. Let's look at nomenclature of carboxylic acids. Just like we did in all of the examples we've seen before, you're going to select the parent compound from the longest chain of carbon atoms, and that chain must contain the carboxyl group. You're going to change the suffix "e" of the alkane to oic, and then add the word acid. A 4-carbon alkane would be butane. A 4-carbon carboxylic acid would be butanoic acid. The carboxyl carbon is always going to be carbon number 1. This is because the carboxyl group is the highest priority functional group. So whenever you see a molecule that has a carboxyl group, that carboxyl group must be part of the parent chain, and the carbonyl carbon must be carbon number 1. Let's look at a few specific examples. Here we have a 1-carbon, a 2-carbon, and a 3-carbon carboxylic acid. Remember that the carboxylate must always be at the end of the molecule, because our last atom is a hydrogen. Hydrogen can't make any more bonds to anything else. I've already told you that the first molecule is formic acid, the second molecule is acetic acid, but they also have systematic names. Those would be methanoic for formic and ethanoic for acetic. The molecule on the right that has 3 carbons would be propanoic acid. So methanoic acid, ethanoic acid and propanoic acid. Propanoic acid you'll also hear called propionic acid. This molecule here has 1, 2, 3, 4 carbons in the parent chain. We also have a methyl group as a substituent, but remember that carbon number 1 must be my carbonyl carbon. So this molecule would be 3-methyl butanoic acid. Our second molecule is a little more complicated. We have a double bond, and we also have an aromatic substituent. I've told you before that that substituent is a phenyl group. So this molecule would be 3-phenyl 2-propenoic acid. The phenyl group is at carbon 3. The double bond is at carbon 2. The common name for this molecule is cinnamic acid, and yes, it does smell like cinnamon. Dicarboxylic acids we name by adding the suffix dioic and the word acid to the parent. So for instance, a 2-carbon dicarboxylic acid would be ethane dioic acid. The more common name or trivial name is oxalic acid. A 3-carbon dicarboxylic acid would be propane dioic acid, and the more common name for that is malonic acid. Here we have 2,3-dihydroxy butane dioic acid, 4 carbons in our parent chain, 2 hydroxyl groups at carbons 2 and 3. This is also known as tartaric acid. And our last example is hexane dioic acid, or adipic acid. Tartaric acid can be found in red wine, and hexane dioic acid is one of the starting materials for the production of nylon. What about aromatic carboxylic acids? You already know that a benzene ring with a carboxylate group is benzoic acid. If we look at our next example here, we have 2-hydroxybenzoic acid. Well, you may remember that a benzene ring with a hydroxy group on it is a phenol. And why didn't I call this 2-carboxyphenol? The reason is that the carboxylic acid is the highest priority functional group. So the carboxylate group wins the name game. So this is named as a substituted benzoic acid rather than a substituted phenol. We can name benzene dicarboxylic acids in a way that's similar to the way we named other dicarboxylic acids. So here we have 1,2 benzene dicarboxylic acid. The 1 and 2 are meant to indicate to you the relative positions of the carboxylate groups. And we have, finally, 1,4 benzene dicarboxylic acid.